Cracking in concrete, common in cement-based materials, leading to high repair costs. And of course, these cracks can make lots of environmental problems. Bacteria in concrete. Bacillus genus bacteria survive in alkaline environments and produce calcium carbonate. Bacterial self-healing uses carbonatizing bacteria to reduce cracks and improve durability. Cracking and repair of concrete. Concrete is strong in compression but weak in tension, leading to cracks. Cracks affect concrete's permeability and resistance to aggressive substances. Repair methods are costly, including shotcrete, resin injection, epoxy, and cementitious repair mortars. Rebuilding bridges in the US costs $20 million to $200 million, with annual maintenance around $2.5 million. Mechanism of bacterial action in concrete. Microorganisms catalyze the hydrolysis of urea into carbonate and ammonia. This forms calcium carbonate deposit on the cell walls of microorganisms. Microorganisms attract cations like Ca2+ from the environment, resulting in calcium carbonate deposition. The article discusses using Sportsarcina pastori as a healing agent in concrete. This bacterium produces calcium carbonate in alkaline environments and is not affected by calcium ion concentration. It is non-pathogenic and spore-forming, obtained from the University of Isfahan. At this slide, we can see the process of our bacteria that we can see the equipment that we used, and our suspensions that we used are urea and calcium chloride. Here we can see the material that we use, like cement, sand, slag, coarse aggregate, and bacteria. Our research methodology includes these three steps. First one, fabrication of specimens. Second, curing of specimens, and third one is testing the specimens. The preparation of samples includes these steps: sampling, mixing plant, create a crack, and processing. The concrete mixing plant is as described in the following tables that we can see them here. In this study, two types of mixtures were used to investigate the effect of bacteria on the healing properties of the samples: natural crack and artificial cracks. In this study, 6 treatment methods were applied to evaluate the healing properties of concrete samples. BCS1, regular sand samples placed in plain water after mold removal. BCS2, regular sand samples placed in water with urea and calcium chloride after mold removal. BCS3, regular sand samples placed in water with bacteria, urea, and calcium chloride after mold removal. ACS1, washed sand samples with bacteria placed in water with urea and calcium chloride after mold removal. ACS2, mineral sand samples with bacteria placed in water with urea and calcium chloride after mold removal. ACS3, washed sand samples with bacteria placed in water with bacteria, urea, and calcium chloride after mold removal. SEM analysis of concrete samples. Concrete samples with a compressive strength of 30 MPa were prepared, polished, and gold-coated. These samples were examined under a scanning electron microscope, or SEM, to capture images and analyze the chemical composition of calcium carbonate deposits. At this slide, we can see the results of SEM test. At this table, we can see the compressive strength of our samples. Enhanced strength. Using bacteria with suitable sand type significantly improves compressive strength. Optimal conditions. ACS3 design shows potential for better load-bearing capacity. Calcium carbonate formation. Bacteria help form calcium carbonate, filling voids and increasing structural integrity. The experimental results show that using bacteria with suitable sand type significantly enhances the compressive strength of concrete samples. The optimal condition in the ACS3 design highlight the potential of biologically enhanced concrete for improved load-bearing capacity. Bacteria play a beneficial role in forming calcium carbonates, which fills voids and increases structural integrity.